this is Tom from anti-proton.com, and here I am today to talk to you about units. This is a quick video. This is not part of my Geiger Counter course. Actually, tomorrow I'm going to be making a video which will be part of my Geiger Counter course, which will cover parts of this, but this is a quick and dirty video. The point of this video is to explain to you folks the difference between things like counts per minute, milliroentgens per hour, microsieverts, counts per second, those sorts of things. All too often I see people not using these units correctly and having various random discussions as to what they mean and various other things. So I thought I'd give you a quick and dirty explanation. Maybe it'll make more sense. Let me cut this off now. Put this down and get out the old marker. First and foremost, before anything else, you must understand what an event on the Geiger counter is. Alright, an event on the Geiger counter would be when the Geiger tube, here's your tube, when your tube is sitting here, it has an outside part and it has an inside part here. One of these is positive and one of these is negative. So positive outside, negative inside. It can be the other way, it depends on the Geiger counter, so on. But there's a potential between these two. Electricity wishes to flow. Electricity cannot flow. The reason it cannot flow is because of the fact that there's a gas in between here and there's no ability for the electricity to move all the way across. There's not enough energy. There's a lot of energy, but not enough energy. When something radioactive, that's red again, let's switch to a different color. When something, I have a lot of red markers. Oh my god. When something flies through the tube like radiation, what it does is it allows a potential electricity to move from one of these to the other one of these, which is then measured in the Geiger counter. Let me give you a quick and dirty explanation of how that works. Basically, a piece of electricity comes in here and hits an atom. Here's my little crappy atom. And what it does is it excites the atom, and it can even cause the atom to release an electron, which can then cause the atom itself to spiral off as just a nucleus, or in reality it actually probably has more electrons around the outside of it. But that electron will shoot off by itself and curve one direction while the nucleus goes the other way, and the nucleus really probably has other electrons around it, because we're not really thinking about hydrogen here, we're actually probably thinking about neon. And between the two of these guys, they're able to cause additional atoms to go through these same kinds of releases and changes in the number of electrons they have, causing an avalanche. It's like a chain reaction, like billiard balls flying across a table. If this goes on for too long and it's too pronounced, it can even cause something in a tube called a glow. But regardless of this effect, you basically have energy, and as the energy goes up, you hit a point called the Geiger plateau. This is the point where the energy is high enough to cause a tick to form, but not so high as to cause a continuous glow in the tube. This in between. Here it's not enough energy to jump across. Here it's too much and it'll either just start going across, or if anything hits it, it will continuously go across. So here's your Geiger plateau right here. So you get the point. Energy is very important to a Geiger counter. You want to probably stay somewhere around here. But energy is not the most important thing in a Geiger counter. Geiger counters, and think of the name. A physicist told me this once. Very important piece of information. What is the name? It is a Geiger counter. It counts. It is not a scintillator or anything other than that. It is a Geiger counter. It detects. It does not measure radiation. By happenstance of various factors in math, it is capable of measuring. It is not automatically going to measure anything. Let me explain. Energy that moves through the air has a certain amount of energy. Things that move through the air have a certain amount of energy, like a photon, an alpha particle, a beta particle, which is just a high-speed electron or a positron or whatever. They have a certain amount of energy to them. That energy has a humongous amount to do with what they're capable of doing. Will the energy be enough to cause the damage to your cell? Will it penetrate your skin or not? That has all to do with the amount of energy and several other effects, such as the spin of the particle, and its electromagnetic characteristics, if it's very, very positively and negatively charged, and also what sorts of things it can interact with. If is it strongly interactive, weakly interactive, is it electromagnetically interactive, is it only gravimetrically interactive, those sorts of things. When you have a Geiger counter, you can count a number of units going through, but you don't have a quality of energy. To get a concept of energy, you have to calibrate your unit. Let us look at a bridge, or actually a road is fine. Here's your road. This is the example I will use. Here's the little dots down the middle. Alright, I have a cat that keeps attacking my tripod, so I shoot the cat with the squirt gun. This makes the cat displeased and he leaves. So if you see me shoot something randomly, it's the cat, because he can't leave the tripod alone. So I don't usually do my videos in this room for this reason. If you were to set up a sensor across the road so that whenever cars drive by, you got a click, and then you counted those clicks. If every single car were exactly the same weight, you would get clicks times the weight of the car times the period of time you're testing equals the total weight per that time. So, if every car weighed 1,000 pounds, or kilos if you want to be into, let's go kilograms so we can be all metric about it. If every single car always weighed 1,000 kilos, then one car times 1,000 kilograms, and let's say that was in 1 minute, 1 minute would equal 1,000 kilograms per minute. That's really simple, right? One car, 1,000 kilograms, 1 minute. And if you knew that every single car weighed 1,000 kilograms, then you would no longer need to know this part right here. You could just simply say 10 cars equals 10,000 kilograms, 100 equals 100,000 kilograms. And the reason for that is because you are calibrated to that car. Every single time a car goes by, you know the weight. Now, look at it like this for a second. If you measure 10 cars going by, and you know that they're always 1,000 kilograms apiece, then you know that you have 10,000 kilograms. There's an extra zero here. In a certain amount of time. But what if 10 cars go by, and they're actually 2,000 kilograms each? What if? What if this happened? 10 cars go by, but they're actually 2,000 kilograms. Well, that's 20,000 kilograms worth of cars. But because you are calibrated for 10,000, meaning that you have determined that one car going by is 1,000 kilograms, you're going to think that you've only gotten 10,000 when it's really 20. Your bridge will collapse, your road will wear too fast, you will be wrong. And you won't even know it. Why? Because your method of calibrating, your method of determining things involves a unit of weight. And the weight isn't always uniform. Now, let's bring this over into Geiger counters for a minute, because it actually makes sense in Geiger counters. Let's get rid of weight for a minute and think about energy. Okay? Most of the units that people use, Grays, Seiverts, Roentgens, rims, rads, all of those things, you know? Most of these units involve energy. Let me give you an example. 1 gray of beta. I say beta because, well, gamma would work too, both of them. There's this other little quality factor thing that comes into play that I'll get into in a moment. But 1 gray of let's go with gamma. 1 gray of gamma is equal to 1 joule of energy deposited into 1 kilogram of matter. If you took this same amount of 1 joule of energy and deposited it into 2 kilograms of matter, that would equal 1/2 of a gray per kilogram, right? Now, if instead you increase this to 2 joules, now we would be back to 1 gray again. You get the idea, right? It's pretty simple. Basically, with a gray, you have energy, energy, G divided into mass, and if you want to say grays per hour, grays per second, grays per minute, then you are further divided into time. This little -1 here means that this stuff is like divided into this, but we don't want to write it like that. Okay, you get the idea, right? Energy divided amongst the mass divided by time. Alright, that's good. Now, so here's my Geiger counter. I want to figure out Roentgens. Oh, there's Japanese radiation around. I'm scanning things. I want to determine Roentgens. I can't. Why can't I? Well, here's why. There could be multiple elements out there right this moment. Cesium-137, strontium-90, iodine-131. Various types of xenon are floating around. Another version of iodine is floating about there. A couple more cesiums. Oh, there could be a whole bunch of other random things. Well, probably not molybdenum. It's probably gone by now. But various other elements are floating around. Even your old uranium, and probably not plutonium, but there could be, in theory, there could be a tiny microscopic drop of it floating around here or there, okay? Every single one of those has a different amount of energy. Yes, strontium-90 and cesium-137 put out similar energies, but they're not the same. So this is all over the place. How can you calculate a unit like a gray if the energy is all over the place? If I had a source disk that was uranium, then sure, I could figure that out in 3 seconds. But I don't. This is not a source disk. I'm not calibrated to it. It is random all over the place. Who knows what? I don't know this, so I can't know a gray. And a Seivert is equal to a gray multiplied by 2 weighting factors. Weighting factors being the type of radiation, which accounts for the differences in that, and the part of the body you're being exposed to. So that's all cool, but wait a minute. This part right here requires knowing the energy. Hell, this part requires knowing the type of radiation. Again, the Geiger counter doesn't tell you the type. You can figure it out. You can figure it out. You can hold up the aluminum piece and the paper piece and the lead piece and go through all that jazz. But even if you figure that out, you still don't know this because you don't know the type of energy and you can't guess. You can't guess. It can be all over the place. But there's more to it than that. Certain Geiger counters have different efficiencies of picking up different radiation. My Geiger counter has a 99% efficiency at picking up uranium-238 standard emissions. But technetium-99m, metastable one that's used by doctors a lot in radiological type therapies and things, I am less than 1% efficient at picking them up. So for every 1 click I get, I'm probably actually getting 99 more clicks. Well, 99 more things going past me, but I don't detect them. So, truly speaking, we can say that with a Geiger counter for an unknown source, which is most of the radiation you're picking up, unless you're in a lab and you have an exact source disk for an unknown source, grays are out the window, they're gone. Can't use them. And if you can't use a gray, then you can't use a Seivert because one's based on the other. Okay? Well, hold on a minute. That's Le Système International stuff, or whatever the hell it is. I can't speak French. Système International. That's basically SI units, metric. What about the old-fashioned type stuff like Roentgens with a big old roll of your R? Well, let's see. What the hell is a Roentgen equal to? Roentgen's equal to, oh, what the hell is it? It's something to do with columns of force. I can't remember what the hell it is. It's basically like a potential force being exerted in a with, what is it? One static unit of force in one like square foot of dry air or something like that. I plead ignorance. I can't remember what the hell Roentgen's actual definition is. I can remember it a little, but not enough for anything valuable. There's my iPad over there, and I'll almost go look it up, but whatever. But who cares? I don't usually use Roentgens anyway. I usually use SI units. But again, Coulomb of force, a charge. When you look up the definition, and you can look it up on Wikipedia. If you look up the definition of Roentgen, you're looking up an energy unit again. Roentgens are out, gone, because you don't know the energy. You can't guess the energy. It's all over the place. It could be in kiloelectron volts, mega electron volts, you don't know. Okay? REM, Roentgen equivalent man. Again, can't use it because it takes Roentgen to figure it out. Or rads, can't figure them out either because a rad requires the understanding of the amount of energy. So, we've killed rads, REMs, Roentgens, Seiverts, Greys, all out because you don't know the energy. And if you don't believe me and you think I'm foolish or naive, go to Wikipedia, go to your science books, any science book you want, look up each one of these, every single one of these, and you will find that each one of them requires a unit of energy. If you know that unit of energy, you have a source disk you bought on the internet and you're zapping it with the Geiger counter, then you're good. You can calibrate your Geiger counter to that source disk. Calibrate it. You're good. Then you can use all of these. Well, you still have to do some more math to figure them out, but the point is you can use them then. If you have a scintillator, hell, you're good to begin with. None of this even matters if you have a scintillator. Okay, so you're saying, well, what the hell am I supposed to do with the Geiger counter? It's got all these, it has all these buttons for Seiverts and millirems and all this other crap, or milliroentgens. No, you don't use any of these. What you need to be doing is you need to be using counts per minute, counts per second. Because this has no unit of energy. This has the frequency something happens given a time. Nothing to do with energy. Nothing. That's it. That's what you need to be using if you don't know the type of energy. Now, you say, wait a minute, and I've heard this explanation before. You have this fancy Geiger counter that's super sensitive, and I got this one over here that's not sensitive. Perhaps if I don't use counts per minute, since they're different, you know, mine's 500 counts per minute, yours is only 50. What if I switch to milliroentgen? They'll be very similar to each other, right? And it's true. If I were to take an item, if I take two Geiger counters that are totally different, and I put down a source in front of them and put them next to it, and these Geiger counters are both calibrated to Cs137 gamma only, like most of them are, but not all, mind you. It is true that their milliroentgen readings that you see will be similar to one another. I think I've even shown it in some of my videos between my two Geiger counters. They're similar, but they are not the same. That is misleading and it is wrong. Geiger counters are meant to be a indicator of the radioactivity of an object based on the properties of your Geiger counter, its geometry, sensitivity, efficiency, and other things. They are not meant to scale between units. That was never something that was supposed to be done. Why this goes on and on and on, I don't know. If you take a class in nuclear physics, you'll figure this out pretty quickly. You can't do it for many reasons. My one Geiger counter versus my other Geiger counter, if we drew this to scale, by the way, not really to scale, but if this unit right here, the one I just showed you, is this big, then my other one, my equivalent in scale, would be like this. LND 712, LND 7313, alright? Much larger by comparison. I know I drew both of them big. Much larger by comparison. Alright? Both have the same gas in them. Massive difference in the size of the mica tubes in the front of them. Response times are going to be very similar, so are the quench times. You have so many factors to take into account. There's another thing to take into account. Distance from the target. Here's your Geiger tube. Here's the object you're looking at. This R represents the distance. You have a certain amount of energy, a certain activity that's coming out of this unit. That'll be measured probably in becquerels. That's decays per second. Bing, 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 bing. You're going to take this much energy, alright, and you're going to divide it. Let me give you the old-fashioned elementary school division symbol. You're going to divide it by this gigantic sphere. So you've got the sphere that you've drawn around here, because at this point, at any point around the sphere, you should be getting about the same reading, right? So that much energy has to have divided into that. And that sphere will be represented by 4 pi r squared. So now you've taken all of this and you've divided it into this, but that's still not good enough. I love brackets and braces. I use them way too much. It's terrible. Also odd symbols and things, I love them. Now you want to divide this. Again, we're going to use elementary school style division symbol to make this simple, by the efficiency. And I'm going to put a bracket around that so you can see it's actually one variable. I just like to write efficiency that way of your Geiger counter. It gets way more complicated than that. Each Geiger counter is a different one of these for an element. They're not going to be held exactly the right distance unless you use a ruler. That's going to probably be about the same unless you're examining something really obscure. It's per second. That's, by the way, that's for counts per second. You'd multiply that by 60 for average counts per minute. There's just so much to take into account. You just can't do it, is all I'm trying to say. So anyway, to put it simply, there really truly is no true such thing as counts per second equals this, or counts per minute equals this number of milliroentgens. There's no equivalence across the board. For your Geiger counter, for a specific calibrated source and a specific set of geometry, that is true. For your Geiger counter, here's the tube, at a fixed length from a source that is shielded to produce only the exact specific type of radiation that you're trying to examine and the exact specific conditions, only then is that true. When these things are true for your Geiger counter, then there will be such thing as a CPM equals milliroentgen multiplied by conversion. We'll call it a conversion constant. That will exist then. And that is what is this thing, that's what this thing attempts to approximate. When I tell it to show me milliroentgens, it's giving me what my counts per minute would be were they in this exact perfect scenario. And it's not infinitely off. It's close. It's not right. And that you can take to the bank. If you do not believe me, if you do not agree with me, and it's fine if you don't agree with me, I'm not saying, you know, whatever, but if you don't believe me, contact a physicist. Call your local university, ask them if this is true. Ask them. So, this has been Tom from anti-proton.com. Tomorrow's video is going to go over this kind of stuff in more detail, but maybe a little bit more operationally speaking, if you wanted to actually use one of these things to detect something. So, bye-bye.